Fine.
Stupid note-taking guy.
Fine. If you
It's recording.
if you draw an altitude,
Say hi to all the people watching.
if you draw an altitude down
Yeah.
to the hypotenuse,
I'm out.
if you draw an altitude down to the hypotenuse of a right triangle. So if I have a right triangle, here's a right triangle, there's a hypotenuse. If I draw an altitude down, recall altitude goes from a vertex to the opposite side at a right angle. Then the two triangles formed are similar to each other and to the original triangle. If you draw an altitude, then the three triangles that you get, the two smaller ones and the larger one we started with, are all similar triangles. Similar meaning that the corresponding angles are congruent and the corresponding sides are all proportional in size. So, one important skill that we would like to have would be identifying some similar triangles that are here. Actually, I have a kind of neat demo here. I made myself a little neat demo, so bear with me.
Wait, I don't know.
Okay.
What happened to the notes?
These are the notes.
Here's a triangle, and I've drawn an altitude from the vertex to the hypotenuse. Notice this, my large triangle is a right triangle, and I've drawn an altitude up a segment from the vertex to the opposite side at a right angle. I claim that the three triangles we have, this small one, this larger one, and then the big one, are all similar, meaning the angles are all congruent. There are three congruent angles, and the corresponding sides are proportional. Let's see if we can identify let's see if we can identify where some of these corresponding angles are. So if I have this big triangle here, hey, there's the big triangle. Okay. There's the big triangle. We're going to look at, how about the smaller triangle? Let's look at the smallest triangle. So if I take the smallest triangle, I've taken the small triangle now. Which angle? It's a work in progress. Okay. Which angle does should this angle match up with in this triangle? Right?
The top.
This guy. Okay. So then what angle here corresponds? What angle does this one match up with? It has to be this guy. So if I were to say, look at this, I could say that I have, if I rotate my triangles just slightly, that this should be at this angle in and so there's still some kinks in the system. But this angle and that angle should be the same, agreed? And then this angle here, no. Guess I should have done some more experimenting with this.
It's okay, we get it.
I was trying. I'm really trying here.
Okay.
This angle and this angle should match with this angle and that angle. How should we rotate this triangle so that it seems to match up? What angle did this one in our larger of the two triangles match up with on the big triangle? Ben?
As if we flip it completely around.
saying.
Am I allowed to do that?
Notice how this triangle came from this piece. So where should this angle? So this angle on the big triangle should match up with which angle on my middle-sized triangle?
One on the bottom.
This one. Okay. So what should this angle match up with? What should this one match up with? The top one. If you could spin it around a little bit. If I spin it around, notice how this angle and this one should match up with our bottom. Top angle should match with the top angle if you just spin them. Now you could have also, reflected this triangle, and now they'll be kind of in the same spot. But the big idea is of the smaller triangle, we're going to have one angle that fits, and the other angle is going to match to the other side. What I'm getting at is that when we write, we're going to eventually try to figure out what some similar triangles are here, and write some similarity statements. So like on our first example here, example A, what would be a similar triangle or a similarity statement that we can make for, say, triangle A, B, C? Triangle ABC is similar to what triangle? Okay, let's get one of them. Andrew? These are two separate examples. Two separate examples. Okay, bring me one. Give me one.
B, D, C.
A, B, C
Oh.
is similar to which triangle?
It's confusing.
No. A, B, C.
A, D, B.
It doesn't matter which one.
A, D, B. A, D, B.
Maybe this will help if we mark the angles. So A, B, C. We start at the 1 mark, go to, okay, let's make maybe a little bit. How about we go to the 90? Sorry. So we go small angle to right angle to middle size angle. Then I could go from, say, if I go from B to right angle to middle size angle, B, small, right, large, middle, small, right, middle, B, D, C. Did someone say that? Yeah, totally. Okay, good. It's also similar to what other triangle? How would we write the similarity statement for this guy? For the middle-sized triangle. I'm going to write the similarity statement now for this triangle. Small angle to right angle to middle angle. ABC is similar to BDC, which is similar to ADB. Okay. As you saw with similarity statements last try, it doesn't matter how you write the first one, but then you have to make sure the other ones fall in step, so that the corresponding parts are in the right spot. So like if you wanted to start by saying, how about triangle CBA would be similar to CDB. What else would be similar to BDA? Let's try it again with this guy. Let's go. How about the smallest triangle first? Triangle. How do you want to write the first similarity statement? Which one do you want to do? Triangle SRW. SRW is similar to triangle T
See, there's 3 triangles.
TRS.
Yeah, that's what it's
I know, it's hard.
Correct.
This is. We did this
I'm gonna have to practice. Very well.
Writing the similarity statements are nice because if you have the similarity statement, then we can actually get the proportions for the sides correct. Similar triangles have proportional sides. That's what's nice about them. So the ratios of the corresponding sides are always the same. So one way to find some missing parts in a triangle that has the altitude drawn to a right triangle with an altitude drawn is we can find some similar triangles and create a proportion that works well for us. So, for example, I could find, how about we start by finding a couple similar triangles, like say, this triangle and this triangle. Well, let's see. What would be does anyone see a proportion we can set up? Anyone see the corresponding sides?
Oh.
So in our triangle here, you have 2 and y.
Y and yeah, Y.
If we have these 2 triangles, and these triangles are both similar to each other, if you have these triangles, and if we label in the corresponding angles, we have this angle is congruent to this angle, and this angle. Those angles are the same, and those angles are the same. So what sides correspond to each other?
Oh, that's easy.
Well, how about the side that's between the 2 hash and the right angle?
2 and whatever that number is.
This side should correspond to this side. It's the side between the right angle and the double hash. The right angle and the double hash. So 2 over y
Yeah, that is it.
should correspond to, oh, how about the side that's between the right angle and the single hash? Y over right angle and single hash. 8.
Geometric mean.
Which, as we saw in algebra review, this is just a geometric mean.
So why is 4?
So once you're here, now you could solve this proportion. Cross multiply and solve. Okay. Well, how about what happens if we don't know? This was if we didn't know like the altitude or the altitude was involved. This time we don't really have the altitude involved. What would these 2 triangles look like? Well, be a couple triangles we could look at to set up. Well, let's see. I see that this triangle here has a couple parts that we know. And do we know 2 things about the small triangle here? We know 2 pieces of information about the small triangle.
Yeah.
We do?
Yes.
We know this. We know that leg is 1. Do you know the hypotenuse of the small triangle?
No.
Do you know this leg of the small triangle?
Well, we know it's equal.
You know it's proportional. Well, okay, so you know this and this are the same, yeah, but we don't know what it is.
Yeah.
That seems like more work. How about if we look at the large triangle? The large triangle has sides of x, right angle,
5.
and then what's the hypotenuse of the large triangle? 5. So what's a proportion we could visually set up with these 2 similar triangles? Well, we could say what? How about 4 right angle and 1 hash, right angle and 1 hash. 4 is to x as x is to single double, single double. Oh look, another geometric mean.
Yay. That's 20.
Or 2 roots of 5. There's going to be 2 geometric mean theorems here. The first is the altitude geometric mean. This says that the altitude drawn down to the hypotenuse is the geometric mean of the parts of the hypotenuse created. Or a formula might be part is to altitude as altitude is to other part. Would be a formula. Would be this formula that comes from this geometric mean theorem that it creates. Correct.
So what's the low part?
Part over altitude
Oh.
is equal to altitude over the other part. So for example, if I don't know the altitude, if I do know the 2 parts of the hypotenuse that it makes, then I can set up, using the geometric mean formula, I can set up a proportion to solve. So for example, here's a part of the hypotenuse that's being created by the altitude. Here's a part of the hypotenuse being created by the altitude. So using my geometric mean formula, I can say part is to altitude as altitude is to other part. And solve. You get the same thing if you did the more visual, draw the triangles, find the corresponding parts and match them up, or if you just use this theory. Sure, let's find what this guy is, and then you can do, 15 over x. Or equivalently, you can say phi over x equals x over 15. Each of those proportions gives you the same value of x. Cross multiply and solve. Okay. Well, we don't know the altitude. Well, we actually can have a geometric mean theorem as well that looks at the legs. The geometric mean theorem for legs is as follows. The geometric mean theorem for legs is as follows. It says that a leg of a right triangle is the geometric mean of the hypotenuse and the part of the hypotenuse adjacent to the leg. Or in formula, this would say that the part over leg is equal to the leg over the hypotenuse. in our first example, that would say, well, let's see, part over leg is leg over hypotenuse. I see a part, I see a leg, and I see a hypotenuse. So this little A over this adjacent leg is equal to that adjacent leg over the whole hypotenuse. Would be a formula you could set up, or an equation you could set up in a proportion to solve for a missing piece. Part over leg is leg over hypotenuse.
But like the full length be 12A. If you have like 5 minutes.
Oh, so this is saying that just this part is A, and this whole thing is 12.
Oh.
So this is, it's saying this, like this smaller piece would be 12 minus A, if you wanted to really set up another equation. So then what would be another equation, what would be a proportion we could set up in our second example? Well, are you using, do we care about the altitude in here?
No.
No, so we're probably going to want to use the second one. Part over leg, leg over hypotenuse. So let's see, let's find a leg and the part of the hypotenuse that it's adjacent to. Looks like X and 9 are our pair here. So part over leg equals that same leg over the hypotenuse, which is 20. Not 11. That would be this smaller part. The whole thing is 9 plus 11, which is 20. Here would be a proportion you could set up and solve to find X. Cross multiply. X squared is 180, so X is square root of 180, which you could simplify.